The next example I'm going to do is similar to number 9 on homework 0. The problem I'm going to work out for you is the integral from 0 to 1/2 of x cosine of pi x. So what we always want to do when we start out an integral problem is see if you can use simplification, or you just know what that integral is without doing a bunch of fancy techniques. So this is one that neither of those easy things are going to apply. So then I'm starting to look at substitution and by parts. So substitution is something to look for sometimes before by parts, but if you tried substitution in this one with your u being the inner function pi x in the simple composite function, note that it wouldn't get you too far because your du would be pi dx, and that does not take care of the x hanging out here. That's times the cosine of pi x. So it really doesn't do a whole lot, and it's not worth pursuing any further because it's not getting us to a point where we can evaluate this integral. So it looks like by parts because we have two functions that are different type, x and cosine of pi x are different types of functions, and you can't do some simplifying or other things to get them together and simplify, and usually by parts is a technique that works well for those types of integrals. So we need to remember a formula for by parts, and the most common one is the integral of u dv is equal to uv minus integral v du. And the nice thing about by parts is we can get started right away with the memorization of LIATE, where each letter stands for a different type of function. So L stands for log, I stands for inverse trig, A stands for algebraic, T stands for trig, and E stands for exponential. So categorize the two factors in your problem, x and cosine pi x, according to what's on this list, and then the highest thing on the list is what we're going to choose for the u in the by parts method. So x is categorized as algebraic, and cosine of pi x is categorized as trig. So since x is higher on that list, that's what you're going to choose for your u. So then taking things from there, the u is something that's going to go in that second part of the formula, which is what we're trying to get to. And we can find the du easily by taking the derivative of u. I'm going to write it in Leibniz notation, du over dx. The derivative of x is 1, and then we can rearrange that by multiplying by the differential dx and get du is dx. So now we have our du, which we'll be able to plug in. The thing that remains is the v. So I set everything as forced and go back to the original integral here, and everything has to be represented by the u dv in that integral. So since we chose x as our u, what's forced is that cosine of pi x dx has to be our dv. So we know our dv and we can find our v from that. So dv is equal to cosine of pi x dx. Now there's a couple ways of handling this. I'm going to show you both. You don't really have to do or know both, but people teach us different ways, learn it different ways, so I'll show you both. dv over dx is something I repackaged up from dividing both sides from the dx. And basically what I'm going to try to do here is undo sort of the process I did to find the du. We can, instead it's dv, and we can go to this backwards process to find v, just like undoing du to get to u. So notice this intermediary step is the same, and then now how do you get from du over dx equals 1 to u equals x? That's not what we did, but how would you do that? You take the antiderivative. So, to get back to v, we take the antiderivative cosine of pi over x. So the antiderivative cosine of pi over x is going to be sine, sort of like sine of pi x. So the antiderivatives, when you take the derivative of that v, you better get your dv over dx or the derivative. So notice that when I take the derivative of v, which is sine of pi x, I get cosine of pi x times pi with the chain rule. So the chain rule, take the derivative of the outer function, which is the sine, and evaluate the inner function, that's the original, and then multiply by the derivative of pi x, which is pi. So that is not exactly the same as cosine of pi x. So what I need to do so that I get exactly that is I'm going to correct my choice of v as 1 over pi times sine of pi x. So trying again, just quickly, the derivative of v then would be 1 over pi times cosine of pi x, chain rule, times that pi, don't forget that, the pi over pi cancels, and then I get exactly cosine of pi over x. Alright, long explanation there. You can forget the plus c. We're in the context of evaluating this integral overall, and so within that context we don't write the plus c. So that is one way of finding the v. Just super quickly, as an aside, another way to show this, and this is actually the way I'm probably going to favor in this class, and it's not the way I favor it in Calc 2 or Calc 1 when I teach it. So just to show it again, a little slightly different way, is finding the antiderivative is the same as taking the integral. So kind of a way to think about this is just taking the integral both sides of that dv equation you started with. And also kind of make a connection here that's important to make. So then the integral dv is v, so you're getting to your v, and then the antiderivative of cosine of pi x is the same as the integral of cosine of pi x. And here, technically, you can use substitution technique if you'd like to. And I'm going to go through the trouble of doing that here in this recording because you can kind of skip through parts you don't care about, or not listen to it if you already know what I'm talking about. But for people that need a little extra help, this is explanation here. So you can do this kind of guess and check exactly like we did up here. Put a little star next to it for a sec, where we went through that process. It's the same thing if you'd like to do that. Technically you can do a substitution if you can't do it in your head. So quickly, with the substitution technique for this integral, we do have a composite function, and we call it u, which is a little confusing in this context because we're overall working on the biparts problem with u meaning something totally different. So I'm going to let the u in substitution equal w, just so we can avoid someone looking at the notes out of context and being confused by that. So I'm going to use w instead of u. So if I let my w, which is like the u in substitution, it's pi over x, or not pi over x, but pi x. And I find the dw from that by taking the derivative, I get pi, and so dw equals pi dx. And then look up here, what we have here is cosine of w, and then the dx is going to be replaced by dw over pi because there's no pi hanging out there. So this is a way to correct for that. And so my dx is equal to dw over pi. So putting that together, my v is going to be the integral of cosine w times dw over pi. And then we're almost there. We just have a constant, 1 over pi, and this amounts to just taking the integral of cosine which is sine. And then finally you put your back substitute and write this in terms of x. Our w is equal to pi x. So a lot of sidetracks there, but this is important to understand. So that was just kind of looking at this a slightly different way. You get the same result. Now we have everything we need to put into the biparts formula. So we're going back to the meat of the problem here. We're going back on track here. So what we're going to do now is the integral is the integral u dv part. Now we're going to write down the part that is the uv minus integral v du. So equals over here u, which is x in our problem, v, which we found over here, is 1 over pi sine of pi x. So this is the u v part. The rest of the formula is minus integral v du. So I'm going to move this down because I ran out of room. I write it down again, 1 over pi sine of pi x, and then the last part is to write down your du. So this is the minus integral v du is simply dx in this one. So we got all written down, and then if we're lucky, this last integral is easy to do. Oh, another thing I just noticed is this is actually a definite integral, so I gotta take care of the fact that I got the little numbers there, what are called limits of integration. So now I'm gonna write this stuff down. I have x over pi times sine of pi x. And I still have to use fundamental theorem of calculus part 2 to plug in. So that's just kind of placeholder telling me that I still need to do that. Now looking at this next integral, we're in pretty good shape here because this is an integral that's pretty easy to do. Not too bad. Sine of pi x. Now you could do substitution, which is all this work I did just over here in the parentheses. Very similar to that, because what we were finding over there was the integral cosine of pi x. So really similar thing here. If you can get to the point where you're not having to do all this work, that would be good. And to note that what this is going to be is sort of like the integral just of sine x, which would be negative cosine, but it's got the original inside stuff, and then it's going to be times 1 over pi. And that's the same type of reasoning we went through to find this v over here when our dv over dx, or derivative of v, was cosine of pi x. So you can kind of go through that process if you can't get it right away. But not going through that whole substitution process. When you get better at this, like you are in Calc 2, then it's best to not write that down at some point if you can. Alright, time to put this stuff together. X over pi times sine of pi x. Got to evaluate that thing. Minus 1 over pi times negative 1 over pi times cosine of pi x. And then we got to evaluate that from 0 to 1/2 as well. Simplify that a bit. Now a tip here, you can just plug in 1/2 here with the fundamental theorem of calculus minus, plug it in the 0, minus, and then do that same thing here. What a lot of people like to do at some point is when you have the same limits of integration like we do 0 and 1/2 for both of these, is you can actually pull it out of the whole thing and treat this whole entire expression as 1 and just plug in 1/2 to the whole thing minus it with a 0 plugged in. So here we go, we got plus 1 over pi squared cosine pi x, and this is what I was saying in words. You can do that, and it tends to be a little bit more streamlined when you do it this way, but you're welcome to do it the other way that I described. Alright, here we go, we're going to plug in the 1/2. So we have 1/2 over pi times sine of pi times 1/2, which is going to be pi over 2, plus 1 over pi squared times cosine of pi over 2 minus the 0 plugged in. So we're going to have 0 over pi times, and then we don't even have to be too careful about this because 0 here, because this is going to be 0 since it's times 0. So, and then we have plus 1 over pi squared times cosine of pi times 0 is 0. We're getting there. Okay, next thing, for finding the sines and cosines of things in exact radians, you should write down an exact result whenever possible. So just a reminder of that. We're going to have 1 over, let's write the 2 pi, 2 down low. So sine of pi over 2 using the unit circle or whatever process you need to. The sine of pi over 2 is going to be 1. And then we have our next term, 1 over pi squared. Cosine of pi over 2 is 0. Minus, and then we had a 0 in this first term, but what do we have here? It's going to be minus 1 over pi over 2. Cosine of 0 is 1. So next we're going to have is 1 over 2 pi. This is times 0, so minus 1 over pi squared. And as far as I'm concerned, that's good enough. It's an exact answer. If you wanted to be fancy, you could write it as 1 fraction, but totally not needed, not worth points, extra points or anything, but that would be pi minus 2 over 2 pi squared in case you care about that kind of thing. So that's it.